guys, let's start the simple harmonic motion. And the first question is angular frequency. Okay, this is question 2 of 9702410 and 17. Okay, let me just show you the cover page. Okay, yeah. So October number 2017, and it's a paper 41. It's a 2-hour paper, and I'm doing question by question so that the video is not a few hours long. So yeah. So state with reference to simple harmonic motion what is meant by angular frequency. Okay, angular frequency is of course the number of oscillations produced per unit time. Let's just write that down. Angular frequency is the number of oscillations produced per unit time. Alright? Okay. A thin metal strip is clamped at one end so that it's horizontal. A load of mass m is attached to this free end. The load causes a displacement s. Okay, everything is here. So we also have a graph. It's displacement against acceleration, right? It's a displacement against acceleration. Usually their acceleration against displacement is plotted, but for some reason now they've plotted displacement against acceleration. It's usually a ax graph, not a xa graph. All right. The displacement of the load before it is made to oscillate. Of course, it is zero, right? Like for example, just imagine a pendulum. Whenever they talk about an oscillation, just imagine a pendulum. For example, a pendulum like this. Unless you give it a push, it won't move, isn't it? So similarly, the amplitude of the oscillations, which is the maximum displacement minus the equilibrium. So the displacement here is the maximum is 3.5, but the midpoint is 2.0, so the displacement is 1.5 centimeter. Show that the load is undergoing simple harmonic motion. Acceleration is proportional to the displacement. And this is shown by the straight line graph. So just because it's a straight line, we know that acceleration is directly proportional to the displacement, or the other way around. It's shown by the straight line. Okay. Acceleration is in the opposite direction, and opposite direction to the displacement, and this is shown by the negative gradient. Right? All right. So now calculate the frequency. Okay, frequency is related to the uh, omega, right? It is omega, which is the, yeah, which is omega, yeah. So for example, A is equal to negative omega square x, right? Okay. Now we've plotted, not x here. Now it's s. Now we plotted the other way around. S is plotted on the y-axis and A is plotted on the x-axis. So we just have to say that S is equal to negative 1 over omega square times A. This is y equal to mx. Okay. So the gradient is equal to negative 1 over omega square is equal to. So now let's just identify 2 points in the graph. One of them can be negative 0.6, 3.0. Another one can be 0.6, 1.0. So we have y2 minus y1 divided by x2 minus x1. So 3 1.0 minus 1.0 over negative 0.6 minus 0.6. So of course we can cancel out the negative signs and do a bit of calculation. So of course straight away I can get this one, and it's equal to, using the calculator, invert it, 0.6, and omega is therefore equal to, just take the square root, 0.774. Now we know omega is 2 pi f is equal to 0.774. F is equal to 0.774 over 2 pi, which gives you 0.123 hertz. So that is the frequency. And what is the time period? Just invert it. You have 8, which means that, yeah, the time period is 8. One oscillation takes 8 seconds. All right, it's quite a slow oscillation. Oh, we are at question 3, and this is gravitation. We'll do this in the next video. So see you guys in the next video.